So recently I made a video in response to, I guess, the Veritasium's Big Misconception About Electricity video, where I was trying to explain, why Veritasium's answer was the way it was, and why that he was correct. But I also kind of did it in a way where I said that he's only correct on a technicality. Like his light bulb was kind of magic, and the energy transfer through the air is going to be very, very small. So if you're lost about what's going on, make sure you watch Veritasium's video first. But yeah, anyways, I think I am completely wrong, and that Veritasium, like before I said that he's technically correct, I think now, after I went through the numbers, that he is 100% completely correct in his like even without a magical light bulb, even without any technicalities. I think he is correct now that I looked at it a bit more. So yeah, so let me explain what's going on. So before we go into it, let me just go over real quick what the problem was. So this was the circuit, a simple electric circuit with a battery and a very, very long wire and a switch. And he's asking, when he flips a switch, how long does it take for the light bulb to turn on? And then, here's the answers, the options he gives. And then, most people would say 1 second, because that's how long it takes for, electricity to flow through the wire back to the, the light bulb from the battery. But the answer is actually 1/c seconds. And I originally agreed with this. And I think a lot of people did agree with this because, we can model this as two wires, two conductors parallel as a bunch of capacitors and inductors. And, just from the initial flipping on the switch, the little capacitors right beside the circuit, like the little capacitors right beside my switch, are going to conduct current. So it's basically on instantaneous change. These are basically short circuits, and then the light bulb will make a little blip, right? So this little blip in brightness. And I said that, yeah, technically the light bulb turned on, but it's going to be a very instantaneous response, and this power is going to be very, very weak. The energy transfer through the air here, like by these coupled capacitances, is going to be very, very small. That while he is technically correct in everything, it's not a realistic kind of scenario from an engineering point of view. But I think I am wrong. And just to continue on, I think even Dave from EEVBlog made the exact same analysis, right? And he had the exact same the little impulse response. But he is actually more correct than I am in that he actually said that he's not going to go into the transmission line analysis, right? So he doesn't tell you anything about the actual transition between the impulse and the steady state. So he says the steady state, yeah, the light bulb's going to be on, just like we all expect after 1 second. And he said on flipping the switch, the impulse is the same as what I had in my simulation. We even had the same simulation, software going on. And it's going to be a little initial blip, right? But he doesn't say anything about the transition between this and the steady state response. So he is more correct than I am in that he didn't say anything wrong. I actually said something wrong. I said that the light bulb's going to blip, and then after 1 second it's going to turn on. And I don't think that is the case anymore. And the reason why is that, a lot of people in the comments said I should probably plug in some real numbers for these inductor and capacitance values. And originally I brushed that off. I was saying that these capacitances and inductances are going to be so small that the energy transfer through the air is going to be minuscule. It's going to be negligible, right? I can just basically ignore it. I just put imaginary values just to show the step response, and we don't actually have to look at the real values. But then now actually, some people said, yeah, you use the real values. They are actually 100% correct, and I am 100% wrong in that the real values are actually kind of surprising. So let's just do a really quick review about transmission lines for those who don't know. So I guess a transmission line is just two parallel conductors. So that's what we have from the question is just two wires that are very, very long running parallel to each other. Here is an infinitesimally small segment of that wire, just a slice through it. And you can see it's basically what I have in my simulation. There's a capacitance between the two wires, and there's an inductance between the two wires. And there's also resistance and conductance, but we said that the wire is perfect. So it has zero resistance and zero leakage between the two conductors, so zero conductance there. So it's just going to be a bunch of inductors and a bunch of capacitors. So this is going to be repeated infinitely many times across the whole wire, many chained together. And that is the model of a transmission line. So also about a transmission line, there's something associated with it that's called the characteristic impedance. That is basically saying that if we have this transmission line with this inductance and this capacitance, so these properties, and it's infinitely long, we could replace that entire transmission line with this impedance, which is just an element with an impedance of this value. And the thing is, if we look at the R and G here, if we say the transmission line is perfect, the R and G are basically zero. So then we get J omega L over J omega C. And then the J omegas cancel out. So the omega is the frequency that we're oscillating the electricity at, and the J is an imaginary number because this is an impedance. But the thing is, the J and omega cancel out. So we'll get this simplified equation here. Write down, if I can highlight it, this thing here. or the characteristic impedance is the square root of L over C. And this is a real number. Like, this is not an imaginary number. It doesn't depend on frequency. It's just a single number. And that is basically a resistor, right? L divided by C square root, that's just a resistor. So from his video here, you could replace the left and right side of his very, very long, almost infinite transmission line, which is basically a resistor. Now, where this model would fail would be once that, like, signal hits the end and reflects back. This model would not, like, model that reflection correctly. But for the initial turning on response, it's basically what the circuit is seeing is just one lumped resistor here and one lumped resistor here. So if we have two resistors, a light bulb and a battery, everyone could see how that would turn on the light bulb. The question was, is the resistance going to be like huge? It's going to be in the megaohms, all right? That's what I assumed at first, and that's why I brushed off actually using real numbers in this question, because I thought that like in the real world, for a transmission line a meter apart, this characteristic impedance is going to be in like the megaohms or something. It's not even going to conduct any current at all. That's going to be enough to light the light bulb. So technically, instantaneously when we turn this on, it's just two resistors and a light bulb, and instantaneously there's going to be a minuscule amount of current through this light bulb, and it's fine. But it's not going to be anything measurable and anything important. It's not. We don't even need to look at it. But if after going through like the real numbers, I think that this is completely wrong. And people who said we should actually use the real numbers are actually 100% correct. So before we delve deeper into the question, I just want to go over a toy example of a very simple transmission line just to show you what the characteristic impedance means. So here I have a transmission line of a characteristic impedance of 50 ohms. So that's L divided by C square root is 50. And that's a very, very common number to use for transmission lines. A lot of them have 50 ohms characteristic impedance. Let's say it has a delay time constant of 30 nanoseconds. At the end, it's short circuited. And the circuit on the left side, I have a battery of 1 volt power source. 1 volt, yeah, and a 50 ohm resistor, right? So on steady state, I expect to see 1 volt across the resistor. But as I said initially, if this is a very, very long transmission line, the initial response of it is that we could replace this whole thing with its characteristic impedance of 50 ohms. So it's just a 50 ohm resistor, and a battery. And if you do, like, of course, simple resistor divider, it's going to be half a volt across our resistor here initially, just based on it being split evenly between two 50s. So that's what we expect. When we turn on the simulation, immediately we're going to get half a volt across a resistor. And then after a while, the signal is going to bounce back, and we're going to reach steady state, and then finally we're going to have 1 volt, as a steady state response. So let's run the simulation. You can see it happening right there. So I'm going to stop the simulation here. You can see initially, exactly as we expected, the voltage across this load, which is what the scope is showing. I should probably have explained that. It's going to be 50 millivolts, so half a volt, and then after steady state, it's going to be 1 volt. So let me just run that again, maybe at a bit slower speed. You can see that the little green color is the electricity flowing through it. The green is kind of faint. Hopefully you guys can see that on the actual video. But yeah, you can see the green is propagating through the circuit. Let me just speed up a tiny bit. It's going to reach the end termination. It's going to reflect back. And then once it reflects back, we're going to get our steady state response, which is going to be our 1 volt across the resistor as we expected, right? So yeah, that's to show you guys. I could just replace the whole thing initially for the initial analysis with its characteristic impedance. Now, what happens if I use something other than 50 ohms? So I chose 50 ohms there is because that was a perfectly matched resistance for the transmission line. So if you use, if the resistance on the left side is exactly the same as the characteristic impedance of the transmission line, then it's perfectly matched. I'm not going to get into like the details about that. Basically, if it's not perfectly matched, you're going to get a bunch of reflections of electricity signals across the whole wire. So here is an example where we have a 5 ohm resistor. So that's not 50 anymore, so it's not going to be matched. We're going to get an initial, voltage across the resistor. That's going to be whatever the resistor divider between 5 and 50, that's going to be. It's going to be some small number. And then at steady state, we expect to see 1 volt still across our resistor because this is basically a short circuit at steady state, right? Sorry, my voice is going after talking so long. But yeah, let's run the simulation. Turn up the speed a bit. You can see, yeah, initially we have some voltage. The green is 90 millivolts. And then slowly it's actually stepping up through many, many steps. You can see that the signal is actually reflecting back and forth across our circuit. And it's taking a lot of these little steps before it even reaches anything close to 1 volt. So right now it's at 776 millivolts, 817 millivolts. It's a lot of reflections, right? It's not just a single forward and back 60 nanosecond reflection. It's taking many, many, many reflections before we reach our steady state voltage that we expect. Now that is with unmatched lower resistance value. Let's pick a very, very high resistance value and reset our simulation and run it. And you can see that, yeah, initially we have 900 millivolts. Then it actually reflects and we get 1.074. So that's above 1 volt. And it's going to bounce around that number for a while. For each reflection we get, we're going to go 9.59, 1.033, whatever. But yeah, so the point is that, yeah, the reflections happen and it's going to take many, many bounces for it to settle on steady state. And the initial voltage that we get is just going to be whatever, like the resistance division here, the resistance. So I can't even speak right now, but like 50 and 500 ohms, you can do the math there to calculate the voltage across that resistor very easily, and you'll find that it will be 909 millivolts, right? All right, now we get to the interesting part. Here is his question again, simulated with way more elements in the model. And I'm going to use more realistic values. And now I say realistic in quotes here because remember I said that only the ratio between L and C matters. So I can multiply the top and bottom by like let's say 1 million. That is important because from the impedance calculator you can see that the L and C are actually like extremely small. It's going to be like in nanohenries and picofarads. And in order to simulate this properly, you're going to need a time step that's very, very small. I don't actually know if the simulator can do it. So we can multiply the top and bottom by like 1 million. And that's just going to change our time constant so we can simulate at a much slower rate. And everything else is still going to be valid. So our L divided by C square root is still going to be somewhere around 700. So 719 for my calculator. Let's just use 750, right? I used, if you go through my simulator and take a look at 562 millihenries and 1 microfarad, you'll get the characteristic impedance of 750. So that's going to be on the right side and on the left side. So the two very long transmission lines from his problem. In this first example, let's use a perfectly matched load. Remember the first, in my toy example, for a perfectly matched load, we had a step where it's half the input voltage, and then after that, the steady state is going to be reached after the signal bounces up from the end back to the source again. So yeah, let's run the simulation and see what happens. Run, and then we're going to flip the switch. So initially, everything is powered onto, the positive potential. Once we flip the switch, you can see immediately we're going to get a response. It's going to be at 6 volts, so I have a 12 volt battery here. And then after the signal reaches the end and bounces back, then we're going to reach a steady state response of 12 volts. It's going to wiggle around there and then hits 12 volts, right? So now instead of a perfectly matched load, let's try something even more realistic. So on DigiKey, I could find a 12 volt tiny little light bulb that runs at like 40 milliamps. That means it has basically a resistance of 300 ohms. So let's plug in a 300 ohm resistor here and see what happens, right? So remember earlier I was using 1,500 ohms, and that is exact perfect match for 2 transmission lines that are 750 ohms in total, 750 ohms each. So in total it's going to be 1,500, and that's a perfect match. And we saw in our tour example that when we have a perfect match, everything is very nice and simple. You got half a volt and then 1 volt, and that's what we saw in our earlier example where we had 6 volts and 12 volts, but now we're going to have an unmatched load of a realistic light bulb that runs at 12 volts that I found on DigiKey, and let's see what happens. So I'm going to flip the switch. So yeah, we're going to have the same initial blip, and then we're going to have 6 milliamps initially on our initial response. And here's the first reflection, so that's going to be like 1 second if we're going to use the entire transmission line length. And then here's another second. And you can see it's slowly ramping up. It's taking several seconds for the signal to bounce back and forth before this light bulb reaches its full 12 volt potential. So now it's at 10 volts. That's already a few seconds in. So it's going like 5 or 6 seconds later before it reaches 10 volts. So one thing I want to address real quick is this blip that I mentioned. So you saw in my earlier simulation that there was an initial kick before we started stepping up, and also I mentioned in my previous video there's this blip, and EEVBlog also has the same blip, and we said that this is caused by the initial capacitances around our load here. That's if we model the transmission line as so, it's really the only capacitances around the load that matters in the end, and that's what causes the blip. We see it in the simulation, but I'm going to say that this is also wrong. So this is kind of scary to say, because I'm going to say maybe both I'm wrong. I'm not scared of saying I'm wrong, but I'm scared of saying an industry expert as Dave is also maybe wrong in this regard. In that this blip is just an artifact of how we made our model here, right? Because we decided to put the capacitor right beside the load. There's no reason why that had to be in that order. The inductor can actually be the one between the load and the wire, right? We could put the inductor here, and if I have a simulator here, let me just delete these wires here. So if I plug in 2 inductors right beside the load, this is completely valid. There's no reason why the capacitor had to come first. We will see that we're going to get a different result. So run, and I flip it on, and you can see that there's no more blip. It's scaled differently. This is 2 volts. It's going to start scaling differently now because there's no initial blip to rescale our y-axis here, but it's slowly scaling up. We see the same steps. Let me stop this. You can see at our initial voltage is still 2 volts as before, and it's stepping up, but we are missing that initial blip. So I think that initial blip is actually an artifact of our simulation. So I would say I was wrong about that blip having anything to do with the question at all. And I think just by extension, Dave from EEVBlog might also be wrong, which is very scary to say for me, right? I'm not afraid of saying that I'm wrong, but I'm afraid of saying that others are wrong in this regard. So on that note, if we're going to go over things that I think maybe were wrong, there's one other thing where like everyone was saying that at 1 second we're going to get the steady state response. Dave said it, I said it in my video, and pretty much everyone in the comments could agree that at 1 second we're going to see the light bulb turn on to its full brightness, right? Clearly that's not the case, right? If we run the simulation, so if I turn it on, yeah, we get the initial 2 volts response. But on the first reflection, this is the equivalent of our the signal traveled all the way to the end of the line, reflected back, and that if this line was 1 second long, then that would take 1 second there, right? At the first reflection, we're only getting 5 volts. We're not getting the full voltage, 12 volts across the load here, right? It's 5.232 volts here, or 5.5 volts maybe. So if this is a 12 volt light bulb, I don't know if it will turn on at 5.5 volts at the first reflection. It might take 8 or 9 volts, so maybe it will take 2 or 3 seconds here before it even gets close to turning on, right? So the definite fact that everyone was saying was definitely true. At 1 second, we're going to see the steady state response. That is not true at all from the simulation. Now for what happens at the light bulb, you could go both ways. You could use Veritasium's more magical light bulb, where it will turn on at any current. In that case, the second we flip the switch, other than that 1/c time delay, basically instantaneously, we're going to get some current through the light bulb, right? And if we're using this magical light bulb at 2 volts, 6 milliamps, it's going to turn on. And I mean, that's not unrealistic here. These are not like picoamps or something that I was thinking we're going to get. These are actually milliamps, and that's enough to turn on an LED. That's a significant amount of power here. I think it was 12 milliwatts or something right here. It's not picowatts or nanowatts that I thought we were going to be getting. But the thing is, if you're going to say we need to use a realistic light bulb that turns on at 12 volts or something close to 12 volts, then at 1 second we're clearly not getting 12 volts. Is that the answer is not 1 second, no matter which way you cut it, right? It's either going to be instantaneously, 1/c, immediately after we turn on the switch, just subtracting that time delay between the switch and the wire here, or it's going to take several reflections in, right? Now you might say that's a lot of technicalities for the rating of my light bulb, with the little step ups in voltages and when it's going to glow or whatever. But what if Veritasium could find a light bulb that has resistance much higher than the characteristic impedance of the transmission line, so above 1.5 k ohms. So remember in our toy example, when we had a much higher resistance, the voltage actually, it was a 1 volt steady state. So it first started at 0.9 volts, and then it bounced to 1.07 volts. So it was already really close to the steady state voltage immediately after flipping the switch. And I think we're going to see pretty much the same situation here. So I'm going to run the simulation, going to flip the switch, stop it. You can see immediately after flipping the switch, we already have 9.2 volts across our load here, and we have 17 milliwatts of power. And that's quite a lot of power. It's way more than enough to light an LED, I think. And 1.8 milliamps flowing through this resistor here. So that's quite a lot of milliamps and a lot of power. And it's not like the picowatts or nanowatts that I was expecting that, the energy to flow across the space to be. So yeah, I think I was completely wrong in that regard. And a lot of people who said that, it's going to be definitely 1 second and then Veritasium was only correct on a technicality, I think everyone is wrong. I think Veritasium is actually correct. Let me just keep running this. You can see that after the first bounce, that's 1 second later, and we could actually peak above 12 volts here as expected, and it's going to bounce around until we reach steady state. So in conclusion, I think my original video, what I was trying to explain, I was actually trying to explain why Veritasium was correct, that it was 1/c seconds. But I think my final conclusion is actually wrong. So even though Veritasium is still correct, I think he is actually more correct than I gave him credit for. I originally said that the light bulb is gonna light up at 1/c seconds, but it's gonna be a blip, and he's technically correct, but maybe from an engineering standpoint, he's maybe the light bulb won't light up. But I think now after plugging in the real numbers, he is even correct on all the way through. But yeah, I thought it was very interesting, and I think a lot of people were hating on Veritasium in saying that he is only technically correct, and he's being misleading by being technically correct, saying like if I say I need to throw a basketball into a hoop, does the planet Jupiter have an impact on my throwing, the basketball? I mean, of course it does. Technically, the Jupiter's gravity extends everywhere, but in practicality, it doesn't. So people were thinking that they were Veritasium was explaining it in that way, but I don't think that's true. I think if you plug in real world numbers, go try it out yourself with your impedance calculator and the characteristic impedance and all that. We'll find that you could get a significant amount of power through this load, and definitely when you flip the switch, just basically instantaneously, just based on the delay time of the 1 meter gap, he's gonna get a light bulb to turn on, and I think he can actually do it in real life. And I think that the original video is definitely very interesting because it got everyone to talk about electricity, and I think as an educator, that's probably the best thing you can do, on top of being correct. Okay, my voice is absolutely starting to die and I cannot talk any longer, but as a small bonus, let's try it again, but with the ends cut open. So we have open circuit on the left and right side. I don't think you can see my cursor, but on the left and right side at the very far ends of the circuit, I have snipped the wires. So now it's open circuit at each end. Oh my god, my voice is killing me. But anyways, let's start with the matched load, so 1.5K. Remember, we could replace on initial boot up, like the circuit doesn't know that it's open at the very end yet, right? So we could replace the entire transmission line as if it was infinite. The circuit has no idea that it's not infinite right now, has no idea what's going on at the end, but we could replace the whole thing with its characteristic impedance as if it was infinite, and it will be 750 ohms, 750 ohms, so it'll be like two 750 ohm resistances, and then 1.5K in the middle. And if you just do the simple voltage divider or whatever, that's basically we're going to get half our input voltage across our load, as expected as from before, exact same thing. And then eventually we expect the steady state to be 0 volts because it's open circuit at both ends, right? So let's run the simulation, flip the switch, initially 6 volts as expected, and then straight down to 0 volts steady state once the reflection reaches back at the load. So completely expected. Maybe we could try something else where we put a 300 ohm light bulb here, reset this. Again, we expect the initial response to be exactly the same as before. It's same as our short-circuited example, where both sides were short-circuited, but now we expect the steady state to be 0. Right, so initial step was 2 volts, exactly the same as before, and then it wobbles around steady state. And then finally, just for completeness, you probably already know the answer for this after looking at all these examples, but for a 5K load where we are above the characteristic impedance, we expect the initial response to be like 9 volts, same as before. So again, this resistor divider 5K, 750, 750. Do the simple math for that. It's around 9 volts, what we had before, and then afterwards it's going to slowly step down to the steady state voltage. So flip the switch, initially 9 volts, 9.2 volts, and then it's going to slowly trickle down to 0 volts at steady state. But I encourage you guys to try it out yourself. You want different configurations of where you put the switch, where you put the battery, and this is the fallstat.com simulator, so it's pretty good. So let me know if there's any other issues, and if you guys think of any other questions or improvements or whatever. I thought this was a very interesting problem, and I need to go get a drink of water. So just some TLDRs. In conclusion, I think the blip, like the little spike from my simulation previously, and from Dave from EEVBlog simulation, they're actually artifacts and they're not real. They just come from the positioning of our inductors and capacitors in our simulation. And I think both me and Dave are wrong in that regard. Ideally, the initial response should be just a clean step function, like it's just a square step, and it'll be a flat top step. It will not be an impulse. That's because the initial response until the 1 second reflection comes back is just going to be two characteristic impedance resistors, right? The two L over C square root characteristic impedances. And if we have 2 resistors and a resistive load, that's just going to give you a clean step response. It's not going to be anything complicated there. The next issue is that at 1 second, we will not see the full brightness of the bulb as people expected if the resistance of this bulb is much smaller than the combined characteristic impedance of the transmission lines. So for example, if I went to DigiKey and found a 12 volt 40 milliamp bulb, that's probably going to have a resistance of 300 ohms when it's on, right? This 300 ohms is much less than the characteristic impedance of the transmission lines here, and we saw that it's going to slowly step up to from 2 volts to 5.5 volts or whatever. So it's basically at the first reflection, it's not going to have the full voltage. It's not going to be its full brightness as everyone expected. We did see a special case where if our resistance of our load is exactly matched to the combined impedance of the transmission lines, we will first see a response that's exactly half our expected voltage, and then after the first reflection at 1 second, it will get the full voltage, and that is going to be exactly the steady state at that point. If the resistance is much higher, then we will get close to full voltage at start, and then it will just slowly like bounce around. It will go actually above the voltage, and then it will bounce around the target voltage a bit. You could try this with like if you do the simulation with a 120 volt battery and a 6K resistor, and then you like put an LED in series there. You'll find that the initial current is going to be like 16 milliamps, which is enough to turn on the LED and not even have to blow it up on like steady state, because that steady state will be at like 20 milliamps with 120 volts, right? So yeah, I mean, it's entirely possible. So I think in my original video, like I was trying to say how Derek in Veritasium's video was actually correct, and he was technically like right. And I think a lot of other videos have also said that, you know, he's technically right. But like I think my original video and all these other videos kind of went about it in a way where he's like, you know, kind of technically correct. And first of all, my explanation as to why he's correct was wrong. I think I was wrong. Correct me if I'm wrong. Maybe I'm right, but maybe I'm wrong in this video. I was right in my original video, but I'm pretty sure I was wrong in my original video, and that Derek is actually more correct than we give him credit for. So I believe that he's correct on all counts, and the question is neither deceptive or requires like technicalities, like, you know, in like a spherical Cal physics kind of way. Like, yeah, like the orbit of Jupiter matters right now for how much I weigh on the scale technically, because gravity is everywhere. But like it doesn't matter in an engineering scenario. So after plugging in real values, we saw that we got really real powers. Like they're not picoamps or picowatts or whatever, right? They're very like significant values across the load. So yeah, I think it's actually possible for him to get this to work in real life. I mean, the only trouble might be the actual resistance of a very long wire. It might not actually be the actual coupling between the wires. It might just be the resistance. But yeah, I think it's a great question. It got everyone to talk about the subject. So yeah, looking forward to more videos like this in the future. And don't subscribe to me. I'm not a content creator or a YouTuber. These are just random one-off videos that I got excited about because I like electricity.